Welcome, everyone. It's great to see this group here for the 2016 Ryerson Lecture. This is a lecture named in honor of Nora and Edward Ryerson. Edward Ryerson was a long-standing trustee of the university, was chairman of the Board of Trustees, but was not only had that type of distinguished position, but he represents a piece of a family connection of the Ryerson family, now the Ranney family, of a connection to the University of Chicago really since its inception. Martin Ryerson became a member of the University of Chicago Board of Trustees in 1892. And the Ryerson and Ranney families have been deeply connected to the university continuously since that time. The first Ryerson Lecture was given in 1974 by John Hope Franklin, and one looks at the collection of speakers and the collection of addresses. One sees, as I've remarked before, not only a history of the University of Chicago's intellectual weight over the last 40 plus years, but actually a intellectual history of what has transpired in this country and beyond in terms of intellectual achievement during that period. We're delighted that the speaker this evening is Sid Nagel. Now, I think most of you know how the speaker is chosen. This is a faculty committee from around the university choosing one faculty member based on a lifetime of distinction that this committee believes the University of Chicago community as a whole would like to hear from and benefit from hearing from. So it is really quite remarkable to emerge from that type of process, and we have Sid here this evening who has emerged. And I will tell you a little bit about Sid. So a young Sid Nagel got a bachelor's degree from Columbia, then went on to Princeton, where he got his PhD in physics, came to the University of Chicago in 1976, is now the Stein-Freiler Distinguished Service Professor in Physics, as well as in the Enrico Fermi Institute and the James Franck Institute. He's been head of the Materials Research Lab, director of the Materials Research Science and Engineering Center. He's been master of the Physical Sciences Collegiate Division and associate dean of the Physical Sciences Division. He's a member of the National Academy of Sciences, the American Academy of Sciences, the winner of the Buckley Prize in Condensed Matter Physics of the American Physical Society, and with all of these honors that reflect his research achievements, he is also a winner of the Quantrell Award for Excellence in Undergraduate Teaching at the University of Chicago. His talk today is entitled Reflections on a Liquid Drop. Sid.
Well, thank you very much, Bob. I mean, this is really an incredible honor to be up here in front of all of you and to think about all the people who have given this lecture before me, some of whom were my mentors and who I miss dearly tonight. What I'd like to tell you about is reflections on a liquid drop, and I use that title because I wanted to get reflections in the sense of, well, there's optics involved in reflecting, and so that was one aspect of the title. And the other part was the liquid drop, which represents a lot of the physics that I'm interested in doing, and which I have been doing over the years. And what I want to try and convince you about is that there's a lot of surprises and science in the study of fluids. And so that's going to be the emphasis of my talk today. So I'm going to start off talking about fluids. I just want to say a few words about this, and that fluids are really a wonderful type of matter. And they're wonderful because for a lot of reasons, but one reason that's particularly interesting for me as a physicist is it's a test bed for many different issues, basic issues in science. And they're relevant at all different scales. And so one of the things that I like about the work that we do is we do work at a tabletop scale, a small thing on a table, but sometimes they have relevance to particle accelerators. Sometimes they have relevance to star formation. So it has relevance over a large scale, and that we can get to study this at this very approachable scale, a human level scale. So what are some of the things that I find interesting about the fluids is, well, if we think about what physics has really been good at over the years, well, we're really good at understanding ordered things. Crystals, for example, where you have an atom that's repeated over and over and over and over again in this beautiful crystalline lattice, and that's very well ordered, and you have a lot of information just because I told you what its crystal structure was. But in a liquid, there is no order of that kind. The atoms are just jumbled. They're moving around past each other all the time, and how do I even begin to use that information to try to understand the properties of that liquid? So disorder is something that we get to look at in a fluid. Another thing that physics is very good at is thinking about linear systems. So, you push something, by linear I mean you push something and the material or thing responds proportional to how much you push it. So you push a little bit and it responds a little bit, you push more and it responds more. So that's linear behavior. But all around us, most things are not linear. So for example, you walk down the street and you bump into someone at one level and you get one response. You bump in just a little harder and you get nonlinear response, okay? So it's all around us, okay? Perhaps my favorite of these examples is this far from equilibrium behavior. So if I give you a box of gas, I can tell you more than you would ever care about knowing about what's in that box of gas. Why? Because it's an equilibrium. I can tell you its pressure, I can tell you its fluctuations, I can tell you everything. I could bore you to death talking about that. And we really understand things about being in equilibrium. But if you look around you, most things are not in equilibrium. The climate is not in equilibrium. What else is not in equilibrium? Well, if you think about it, well, you're not in equilibrium. If you were in equilibrium, you'd be dead. And not only dead, you'd be homogeneous, which is a very boring kind of dead. And so all of biology, in some sense, is geared to trying to keep us away from this bland kind of equilibrium. And so this is something that we get to see the beginnings of in studying fluids. Another thing is looking at patterns. And so patterns are formed in fluids, and we see patterns all around us. And so this is one of the things that we particularly appreciate about fluids, is that we can begin to see and understand pattern formation in this kind of a system. Another aspect of fluids is that they also span this incredible range. And they span a range of rigidity. For example, in some sense, the gas in this room is a fluid, and it spans all the way from there to glass. And so this is a piece of glass, and all of that is a kind of a fluid. This is just a glass that was cooled down. And so, again, by studying fluids, we get to see something about that transition. And so one of the things that you can begin to think of these things more generally in terms of not just liquids, but what other things are kind of fluid-like. And so one of the things that we studied over the year, and so this is a lot with Heinrich Jaeger, who's here, I think, in the audience someplace, is just a pile of mustard seeds. So here's a pile of mustard seeds, and it's kind of stable. It's rigid, it's holding its shape, but I just turn it a little bit, and it suddenly starts to flow. Okay, and so this is a kind of a fluid. It's a granular fluid, and it obeys some of the same rules that we have in ordinary fluids, but we get to see this in different contexts. And I will pass this around, so when you get this, you can, and if you shake it a lot, you'll get full of static electricity and ruin the whole thing. But that's for you to do. I leave it to you. Okay, so this leads to the idea of when this thing suddenly gets rigid, then things get jammed, and the granular system no longer can move. And so that's also been something that I've been very interested in over the years, is the jamming, this idea of this non-equilibrium solid, and this gets us to study other very important aspects of what is a very, very rough free energy landscape, which is something that lots of different aspects of science try to study, but here again, we have something concrete that we can begin to get our hands on. So this is one aspect of why I like fluids, but there's another aspect, and that's because surprises abound everywhere. And no matter where you look, I'm always astonished by what kinds of things pop out from the experiments that we're doing. And so not only does these things have surprises, and the structures that these fluids form, really, if you think about it, they form the texture of our world, and that gives us the appreciation for the world around us. But it also has very elegant features, and that's part of what I want to express tonight. It's something about the elegance that these kinds of fluid experiments that we try to do in our lab, how you can appreciate them on a broad level. And that's what I hope I'll be able to explain broadly. And so I know this is probably a wrong use of the word, and I know it's, I was told by my philosopher friends that Plato meant something else by wonder, but still I like this quote that philosophy begins in wonder. And also what I hope tonight is that some of the experiments that we're talking about today begin in wonder. We see something and it just grabs us in some wondrous fashion. So let me start off by one kind of feature that we see in the world around us, these structures. And this is something which I'll call dilation, symmetry, and the penetration of space. Okay? And so I have here a few pictures, and so you see tree branches in winter. You see a view of river networks from an airplane. You see a discharge of what's called beam trees from the particle physicists. You see blood vessels, and you see diffusion limited aggregation, a la Tom Witten's work. So all of these things have a certain kind of structure which we see repeated in all of these different guises. They all have this kind of tree-like behavior. And what are they trying to do? Well, in the case of the tree, it's trying to get all the oxygen it can and all the nutrients in the air. And so it tries to spread out and get all of that. In the case of the river networks, water is coming down everywhere, and you have to try and collect all that water efficiently and get it out to the ocean. In the case of this discharge, you've put in what you've done here is you just bombarded a piece of plastic with electrons, and it's just charged up, and you ground it, and suddenly all those electrons try to go away, and they go off to the ground, leaving these patterns left in the plastic. And likewise, in the blood vessels, there you're trying to get food and oxygen to all the different parts of your body. So this is what is a penetration of space. I'm trying to get things everywhere. And what did I mean by dilation symmetry is that how does it do this? It takes one little piece of that structure, and you can blow that piece up, and it looks like the larger structure. That is, it's repeated on different scales. So I'm dilating the object, and when I've dilated it, that is, I've expanded it, it looks the same as it did before the expansion. So that's the idea of this dilation symmetry of space. It's a symmetry like other symmetries, but it's one we may not have thought of as a symmetry before, but it's a symmetry nonetheless. So what I want to do is I want to say, how can we study this and really get to the bottom of some of the issues here in an experiment? And so the one that I want to talk about is called a viscous-fingering instability. And the idea here is we have two glass plates that are large, and they're separated by a very narrow gap. And then in the center of the plate, we push in one fluid, and so that covers the entire plate. And then we change the fluid, and I now start putting in what I'm calling the inner fluid. So I'm looking down on top of the plate, and you see the whole region is filled with an outer fluid, and now I start pumping an inner fluid into the center. And what you see is what you might think is a boring effect. That is, that blue region, as I just pump in that fluid, it just expands as a circle. So let's see that happen in real life. So let's see if I can do this here. Okay, so what I'm going to do is I'm going to take a little bit of paint and put that down on this plate. And now, as I'm going to put this other piece of plastic above this, and let's see what happens. So as it goes down, you see it's just going out as a nice circle. Right? So it's just as I told you. It's just a beautiful, nice circle that starts to go out. But now, what happens when I take these plates apart? So now you get something that's really quite different and has a beautiful structure involved in it, and it has this tree-like pattern. So it's something that you can do fairly easily if you get the right paint and so this is the kind of experiment that I want to think about now. And so we're going to do this in a more controlled fashion now. And so what we're going to do now is I'm going to, or actually I should say who really did it is Irmgard Bischofberger, a wonderful postdoc of mine. So in that hose in the center, we're going to start, it's already filled up with the outer fluid. And this outer fluid is the one that is more viscous, just like the paint was more viscous in this case. And now I'm going to try to intrude a less viscous fluid, which is like the air rushing into that more viscous fluid. So the air was the fluid, low viscosity fluid, penetrating into the more viscous one. You've got this instability. Let's see what happens in this case. And so now you start pumping, and you see that indeed you do get all of these beautiful fingering patterns. It's one of the standard instabilities that we see, viscous fingering instability. It's been around and studied heavily since 1958, when great theoretician and experimentalist worked at this, and it's become really the basic way we understand a whole lot of instabilities of this kind, fluid instabilities in terms of, and pattern formation in terms of this behavior. Okay, so what is the thing that I want to emphasize here was, well, you get this thing going out, it forms fingers. As the fingers form, they form more fingers. As they form, more fingers come again. So you get this level upon level upon level of fingers, and it gives you a rather beautiful pattern at the end. But the one thing that's trying to stabilize this, the only thing that we know that really is stabilizing this structure at all, is the fact that there's surface tension. So those of you who don't know surface tension, you are familiar with it. That is, you take a liquid in the air, and if there's surface tension, that liquid will try to ball up into a sphere. It does not like to have extra surface area, so it tries to coalesce into a single, as smooth an object, a spherical object as possible. So that's all that's happening here, is that this surface tension is stabilizing this behavior. And so what we wanted to do was look at what would happen if we take the surface tension away. And so that's what this set of pictures is trying to show you, is that it has a very surprising effect. So I told you when I take the surface tension away, it should get really unstable, because that was the only stabilizing term. But now we take the surface tension away, so on the top line, I have ordinary fluids that are having this viscous fingering. On the bottom line, I have pairs of fluids inside and out which have no surface tension between them. And look at them, that is, in all cases, the one that was above it that had surface tension is, in all senses, more unstable than the one down below, which had no surface tension. So this is one of the surprises that hit us. So well, how could this possibly be the case? The stabilizing term, you remove it, and now it becomes more stable rather than unstable. Okay, so that's one of the surprises that came from this. But there's another surprise that you can kind of see here. And if I were to ask you, what do you want to look at in this, and what's interesting, is if you go from left to right, there's a progression in these shapes. On the left, it's almost all fingers everywhere. On the right, you see a big round circular region in the center which is fully displaced, and just a few knobby fingers around the edge. Okay. So there's another shape that's coming in here that we had not appreciated before. That is that once you know that there is this inner fluid that's governed by something else that we hadn't considered previously, this viscosity ratio between the inner and the outer fluids, you now have another length scale on which you can start to compare things. So if you ask, what is the global feature of this? I mean, you would certainly ask, say, well, what is the width of those fingers, which is what people had studied previously. But the other thing is, you would certainly say, wow, it's that we have this enormous region in the center where there's complete displacement, where it's totally stable. So this is one of the features that comes out of this. And so it says that there's a new way of studying these behaviors, these patterns, and that because there's a new length scale emerges, and this is what determines the global patterns of the problem. Now, I should just stop here for a second and say, but what's happening here is you begin to see in this, for the case where no surface tension, there are these stubby little things that come out. And so that's somehow a different regime, and we call those, instead of fingers, we call those toes, because they kind of remind us of toes. And what I just want to show you is the two movies of what happens in the ordinary fingering regime here. And this is the kind of thing you saw previously. It just spreads out, fingers forming fingers forming fingers ad infinitum. And now when we look at the toe regime, something quite different is happening. That is, it does form the toes. It does go unstable, but then it never goes unstable again. And so once a toe forms, it somehow turns off the instability that formed it. So this is a very unusual type of instability that you would think, well, why doesn't it keep forming instability just like the left-hand side one did? And so, this is of possible interest, but I want to emphasize what's new about this and why this is somehow an intrinsically interesting feature, and that there's a kind of pattern that you're all very familiar with in your life. I mean, it's called proportionate growth, and it's the behavior that you all know because you all grew up from little kids. Well, I hope you grew up, but I mean, you start off as little kids and now you're adults, and your shape has remained the same throughout that. As you can tell very often who the kid parent, which is the kid picture of the adult, even though the human being or any mammal has grown many times its original length. So this is a very common kind of pattern formation, but we have no examples of this in a physical world. So all of biology uses it, but we don't have any physics examples of this until this one. And so what I'm showing you here are three pictures of the one movie of the toe formation regime. And you see these are just three different times. And at the beginning, there's a red, it's enclosed in that red region, black region, and finally the full system is the blue region. And if we put them, just blow them up so that they all look the same shape, the same size, the same overall size, you can see that this one can be placed right on top of this one with hardly any changes at all. So this is now the first example, and as far as I know, the only example we now know outside of the biological regime where you have this kind of pattern formation. So it's a new kind of pattern formation that we begin to be able to study in the physics arena, physical sciences arena, that may be able to shed light on something that we've all been very familiar with but never had any idea of how this could take place. So I now want to switch over and talk about another kind of behavior. This is the also nonlinear dynamics in fluids. And the question is, how do drops break apart? And so here is a liquid drop of water just falling. And what I want to understand is something, how does that drop of water which was at one point singly connected, break into two. So clearly, for the mathematicians in the audience, Bob, it's a change in topology, right? It changed the topology. It was singly connected. Now it's two separate pieces. So that's one thing. But the other thing is that, and I don't want to minimize the importance of that, but the thing that really is interesting to us from our point of view is that there's a singularity associated with that change in structure. And so if you think about this, you have this long neck of fluid holding the fluid on top, connecting it to the fluid on the bottom, that drop that's going to break off. And as this thing breaks apart, that neck has to, at some point, get thinner and thinner and thinner and thinner until the radius of that neck goes to 0. If it didn't go to 0, then it would still be connected. So the fact that it broke apart means that it had to, some point, that neck had to shrink to nothing. Right? So how do you try to understand this? Well, what you would do is you would take your computer, simulate this thing, and you would get it at some shape, and then say, well, that's not close enough, so you would work much harder to get a little bit closer, to get this thing a little closer to breaking it off. But you have to work harder because it's smaller and this is still big, so you work harder again, and you get a little closer, and you work harder again, and a little bit closer. And it's Zeno's paradox all over again. No matter how hard you work, you don't get to the other side of the singularity. You just approach it. And so, computers are all over the place trying to figure this out, but then you look outside the window, and there's a drop hanging from the eave, and it just falls. I mean, it doesn't try to figure out, well, what should I do now? And so the idea here is that, well, gee, there's something that we don't really understand about how to treat these singularities in order to do physics with it. That is, this is something that's missing, and in order to really understand this, we have to understand the nature of that kind of a singularity. And as I promised, these things are relevant to lots of different scales. And so this is probably the most famous picture from the Hubble Space Telescope of the pillars of creation. So these are star-forming regions which eventually will break apart and forming little stars in there. And so the idea here is, again, you have this object which has to shrink to nothing between these two regions that are then separated. Okay, so this is an example. So you see this at the celestial scale. You can see at the nuclear scale where nuclei break apart. But we get to study this at this beautiful scale right in front of our noses, on a tabletop, and be able to observe it with experiments, simulation, and theory all together. And that's a very powerful combination of things to make it all work. So what is how does this drop start to go unstable? And this is, again, one of the canonical instabilities called the Rayleigh-Plateau instability in fluid dynamics. But it's a simple thing to ask. So suppose I take a fluid, and I have it in the shape of a cylinder. That's what that neck is. It's forming a cylinder. And I want to ask, is that cylinder now going to be stable? And you would say, no, I just told you that the surface tension is going to try and make it into a ball. But no, I'm not going to allow that. I'm going to make you hold it at the ends so the ends cannot come in. And now I'm going to ask, is that cylinder stable? And it's a simple mathematics question of asking, if I keep the volume of that cylinder fixed, because the water can't go anywhere, it has to be there, which surface enclosing this will have more surface area or less surface area? And so the perturbation I'm going to put on is I start off with the cylinder, and now I just make it a little bigger here, a little smaller in the middle, and a little bigger out here. And you compute the area of that surface area, and that's actually less than the area of the original cylinder. And so it'll flow in that direction if this length is long enough. Okay, and so that's why this drop starts to go unstable. That is, that's the beginnings of how this drop is breaking apart. And so this is the, as I said, the Rayleigh-Plateau instability. You've all seen this. And so you can stick your fingers in your mouth and get some spit on it. And I'm not allowed to say that here. Okay, some saliva on it. And now you spread your fingers. Okay, so tonight, I want you all to go into your bathroom and lock the door so no one can watch you do this. And then when you're sure no one is watching, stick your fingers in your mouth and spread them apart a little bit, and you'll see a little thread of fluid between your fingers, and that will start as a thread, and then it'll start having a little ball in the center in between these two things. And so this is the Rayleigh plateau instability. So I suspected you wouldn't be brave enough to do that in front of everyone, but I'm up here, you're okay. And so I have a picture of that for you. And so this is a bolus spider, and so this is a very wonderful kind of spider. It doesn't build its web, but it does secrete its gooey stuff from I don't know how, but it creates this gooey stuff. And the fly comes along, and it goes whoop, and it does then captures the fly, and then it does what spiders do to flies. But the reason I get to show it to you here is because you can see this thing just hanging here, and what you see is instead of this long, thin, smooth thread, you see it with all these bulges on it. And that's the Rayleigh plateau instability that I just told you about. You've seen it on a beautiful summer morning after a dew at night, and you see a spider's web, and you see it's all decorated with little balls. That's the Rayleigh plateau instability, again, in that guise. So that's the beginning of the instability. So how does it start to break apart? Okay, so or was the final part of its breaking apart. And so what I show here are just two photographs of this drop in the process of breaking apart. So this neck has gotten arbitrarily thin, and it's just at the last part that we could actually photograph it before it fell apart. And you see I have two images here, and I can't really tell the difference between them. They look, as far as their structure, they look essentially identical to me. And so what I have to do is show you where did these images come from. And so in the next picture, I have, I'll just show it to you. This is where they came from. So I was showing this region right here at the bottom, and this region here, and that's all I showed you. But I just made it so you could just see that region, and they really look the same. But what is this picture on the right? That was just a picture of the drop upside down. And so there was really from images that look like this. This was the first one, and then the big drop breaks away, and then this neck of fluid starts to disconnect from the drop that's left on the top of this of the plate. And I've just turned it upside down, but now you see what this structure looks like. In the left-hand one, we have a cone basically pointing into a sphere. Okay. On the right, I have a cone pointing into a sphere. But in this case, the cone is pointing in the direction of gravity, downwards. In this case, the cone was pointing upwards, opposite gravity. So somehow, the way this thing was forced didn't have anything to do with what that final singularity looked like. It somehow managed to do something that was quite universal, irrespective of by changing different parameters about the problem. In this case, which direction gravity was pointing in is distinct from the singularity. Okay, so that's what we wanted to explore, is to what extent do you get this universal behavior in this drop breakup problem. And so there are lots of different drops and different kinds of drops, and they're each unhappy in their own way. Okay, and so what I show you here is this one on the left. This is just water falling in air. That's the one I just showed you. This one next to it is a liquid of water and glycerol falling into air. So it's more viscous than the water. So viscosity, for those of you, is, if I run my finger through water, it's easy to do it. If I run it through honey, there's a lot of drag on it, and that's because honey has a larger viscosity. So that's what. So this is glycerol and water. Now, for those of you who don't know glycerol is what you go to the drugstore and you get and you mix it into making soap bubbles, then making them rigid for your kids. That's one way of doing it. You also probably, I've been told, have a more intimate relationship with glycerol because McDonald's is supposed to put in their shakes to give it that je ne sais quoi de McDonald's. I mean, they call it body, we call it viscosity, but it's the same thing, okay? So that's this one here. This one over here is pure glycerol falling into a vat of a fluid on the outside that's roughly the same viscosity. It's an oil. And on the far right, we see a water drop falling into a very viscous outer liquid. And I don't know if you can see in the back, but this drop here on the right, there's still a connection between the water on top and the water in the drop. And that's what's giving it that nice conical shape. And this is how nature decides is the right way to break a drop apart. I mean, so it's kind of bizarre to me that nature goes to all this trouble to break a drop. But what do we try to do as experimentalists? And so we get to vary things. So I get to vary the inner viscosity of the fluid, the inner viscosity of the inner fluid, the viscosity of the outer fluid. In some cases, air, which is a fluid but low viscosity, or water or glycerol, something that has a higher viscosity. I get to vary the densities of these fluids. So that tells me how much forcing due to gravity there is or how much inertia it is to have the fluids move. I can vary that surface tension between one fluid and the outer fluid. So that's another tool that I have as an experimentalist. And finally, I can talk about the nozzle diameter and do this at different diameters. Okay, so these are the parameters that I get to have as an experimentalist to go into this problem and try to examine what is really going on in this case. So each of these drops looks different because I've tuned it to be in my experimental window by changing these parameters to get different regimes in here. So what I want to now try and do is try to get one notion of how should we think about these shapes. How does this transition take place, the flows in this drop? And so it has this idea of scale invariance, and so I hope I'll be able to get this idea across. So the idea is that as the breakup occurs, that neck is getting smaller and smaller and smaller, thinner. That's what I emphasized at the beginning. It's going to zero. And so it's getting smaller than any other length scale, except, of course, the atomic scale, which I'm not looking at the moment. This is all at a much larger scale than the atomic scale. So I'm not examining that, but I'm looking at the hydrodynamic lengths in the problem. And this is getting smaller than any of those length scales because it's going to zero at that point. Well, if it's smaller than any of those length scales, then the idea is the dynamics in that region cannot depend on any of those other length scales before. Now, why should you believe that? Where does that idea come? So think of the following. Suppose you have rain that comes down on a mountainside. There are mountains out west, so there are mountains out there. The rain came down, and they flow into rivers. And these mighty rivers cross the continent. They get to the Gulf, and in the Gulf, then they break up into smaller rivers, streams, rivulets, and finally the water flows between two little pebbles in the stream. And so my question for you is, does the way the water flows between those two pebbles depend on the fact that it originally came from a mountainside? It doesn't seem likely, right? I mean, how could it remember that? I mean, that information is long lost because the scales are so different. This is basically the idea of the scale invariance that I'm talking about here, is that you've lost this idea of being able to that there's any memory of what its initial conditions were at the point where this thing is really breaking apart. But so the flow in this region only depends on the radius of that neck itself. That's the only thing left. But then you ask, well, what does that neck radius depend on? Well, that depended on the flow. Right? That's what causes it. which depends on the radius, which depends on the flow, which depends radius, flow, radius, flow, radius, flow, radius, flow, radius, flow, all the way down. Okay, so what I've constructed for you here is a fractal sentence. I blow up any region of part of the sentence, and I get the original sentence back. Right? That's the idea. So it should remind you of what I started out with the trees. I blow up one region of the trees, and I get something that looks like the original tree back at the end. So what is this saying? So the idea here is that the mathematics behind treating these equations also have this kind of self-similar structure. And I blow up any part of it, but now I get to blow it up in two ways, along the length or along the radius. And those are two separate things that I get to expand or contract if I want to go closer to the singularity. And this is the idea of what the experiment then tries to do, to try and understand this, see if this is the right way of thinking about the drop breakup. So now I have data here, and the reason for the data is not for you to actually look at the data, but in an audience like this, I mean, I don't want you to think about the data so much, but you should realize that as a physicist, that's what we do. I mean, we do take data. We don't just take pretty pictures, but it's the data that's important. And so, I mean, this stands in for lots and lots of data that is been taken on all of these things, but you should just get an idea of, that yes, you can, from these pictures, you can begin to get real data coming out, and this data then can really confront these theories that in a concrete way. And so there's something universal behind this, and all we have to do is, once we know that universal function, we want to go close to the singularity, I just shrink it in one direction, I shrink it by perhaps something different in the other direction, but I do that over and over and over again, and that's what the mathematical solution at the singularity is supposed to look like. And so this is data that's supposed to verify that. Now, remember, so that makes it kind of a simple story, and it looks all well and good. And then, of course, there's the one experiment too many. And so this experiment is that this picture you've seen before, this is just the drop of water falling in air at the point of breaking up. What would happen if I completely inverted the problem? That is, instead of having water on the inside and air on the outside, I have air on the inside and water on the outside. So basically what I'm having is an air bubble in water rising. And so everything should be the same. The surface tension is the same. The densities are the same. Just what was in was now out, and what was out is now in. That's the only difference that we've done. And so now let's look at what this image, this movie looks like. So this is the air bubble rising. It's shrinking. You can see the little drop in the middle hit the top and came back down again. It's a lovely effect. And what I want to emphasize here is that we did this experiment with extreme care. And why am I emphasizing it here? Well, the other ones, I didn't have to be that careful, but this one, we really made this a very circular nozzle. We really tried to level it very carefully, because if we didn't, then something very different happened. And so the story was that I had this graduate student who was working on this, and was always coming, looked very perturbed, but he would show me the stuff, and it never looked quite good. And I asked him, well, what's going on? Yes, I know they don't look symmetric, but I'm doing the best I can to make them symmetric. But the whole point was that they were not symmetric when they were not carefully leveled and so forth. And so this was the crucial aspect of this problem. And so now to show that in all its glory, what we've done is we now take a slot nozzle instead of a circular nozzle. We blow the air out, and I'm just concentrating on the neck region here. And this white thing is just because we're lighting this from the back. It's just the optics of the thing. It's nothing inside the drop. And so now we can see what this thing looks like. So we'll watch the whole thing through. There's nothing symmetric looking about that at all now. And if you look at this, stop it right there, you can see that this thing really looks like it's being torn from one side or another as this thing is ripped apart. Remind you, what's being torn here? Air and water. I mean, there are no two things I know that's less likely to have a tearing type of transition associated with it. And so this is saying that there's a new kind of behavior. It is a in the lingo we use, a universality class, that this is part of it. But it has different features in that this kind of breakup event remembers everything about its past, whereas the other ones forgot it. That's why I didn't have to be so careful about those original experiments. And so just to see, again, a piece of data to show that you can actually measure how this drop neck is oscillating back and forth as this thing goes off to the breakup point. And so this was a tour de force experiment by Nathan Keim, and the theory was done by Wendy Zhang and her student Laura Schmidt. Okay, so this is one aspect of the drop problem. But what happens after the drop breaks away? Well, it falls, and finally it hits something and splashes. Right? And so what could possibly be interesting in splashing? And so let's take a look at a drop that is going to undergo splashing. So this drop is just a tiny little drop, 3.5 millimeters in diameter. It's falling from roughly this height. So it's going to hit a smooth, dry glass microscope slide at a few meters per second. Everything is just normal stuff. Again, the white thing in the middle is just because it is lit from behind, and so it's just the optics of the system. There's nothing inside the drop. It's just an alcohol drop falling. And as it falls, you will see this gray area is the microscope slide, and you'll see its reflection in that as time goes on. So here it goes. So it comes down, it hits, then it spreads out and forms this beautiful corona, which then breaks up. I mean, I really kind of like that, so I'm going to do it again. So we should all watch this. So here it comes. As soon as it hits, it breaks up. Pow. And it goes out, okay? So this is how water splashes, or liquid splash on a surface. And so why does it splash? What controls splashing? So one of the things certainly is how fast it's falling and how big is that drop. Because if I took a tiny little drop and laid it down ever so carefully on a surface, we know it wouldn't splash. It's only splashing because it's going fast enough or it's large enough. Also, you would think, well, it should depend on that surface tension. That's the thing that's trying to hold it together. Or the viscosity, how easily this stuff flows in these different directions. Okay, so these are the things about the liquid. And now I've finished everything about the liquid. So how about the substrate? Well, the substrate, is it smooth or is it rough? Is it wet or is it dry? Is it hard or is it soft? And now I've basically said everything about the substrate there is. So that's about all there is. Now, I didn't say anything about the air in the room because it doesn't matter, right? I mean, I don't feel it. And the last time you probably felt anything but the air was when you were worried about the air was when you were running up a flight of stairs and you were out of breath, not because the air was in your face, but because you just needed the oxygen. So, but we do know that if you take your hand and put it outside the window of a moving car, you will feel drag on your hand, and your hand will be pulled backwards. Okay? And so we thought, well, maybe the same thing would happen here. That is, if we take the air away, we'd really be able to see a wonderful splash, something really much more dramatic than what I've shown you here. So let's see what happens when we do that. So for the third time, you're going to see the splashing on the left. Here it comes. You see its image, splashes, and it goes and breaks up, and then it goes off. So now we're going to do exactly the same experiment. It's the same drop of liquid falling from the same height onto the same smooth glass microscope slide. Everything is the same except that we took some of the air out. It's 1/3 atmospheric pressure. So this would be the air pressure you would get at the top of Mount Everest. So you could live in this thing. You wouldn't be happy, but you could live there, okay? So now what does this look like? Okay, so be ready for the big splash. Okay, so here it comes. We're going to hit that plate, and we're going to watch the splash come. So when we saw that, I mean, we first started laughing hysterically, and about a month or two later, we picked ourselves off the floor and asked the question that Robbie asked, well, who ordered that? I mean, where did this come from, right? This was not supposed to happen. Of course, I knew what was going to happen, and I misled you. I apologize for that. But I was telling you the same things that I thought before we did the experiment. It wasn't, I misled you in the same way that we were misled by our expectations. So, the point of this is this was a, people have been doing studies of photography of splashing for over 100 years. Worthington did these absolutely amazing photographs of splashing drops before there was good chemistry to do it. I mean, they were really amazing that he was able to do this. And in that last 100 years, no one thought to take the air out because it was a stupid experiment. It really was a stupid experiment. That is, the air could not matter. I mean, for all the reasons I just told you, and for those of you who cognoscenti in the audience would say, and we know that if we take lower the pressure, the viscosity of the air doesn't change. So it really shouldn't have mattered at all. And yet what we found out is that this is the control parameter for the problem. That is, you take the air out, and I can stop this thing from splashing. So what happens now if I go to a more viscous fluid? And so this is exactly the same experiment, just at a higher viscosity, 10 times higher viscosity. And so I drop it, and it's just spreading smoothly on this plate. Nothing is happening, so let's just finish the movie. Oops, I misled you again. But it's very different morphology. Right now it's spreading slowly on the surface before it starts to splash later. Does air still matter? So now we take the air out, and what you see is, yes, the air is still the control parameter that if I take the air away, the thing will stop splashing. So all of these things are features of this drop splashing, that the air is a control parameter, unexpected as it may have been. But it's still the control parameter for what's stopping the thing from splashing. So I think I'm running a little bit out of time, so I'm going to skip this and just go to this one last thing, just to give you one last idea. So in order to investigate this, what kind of things do we do? What we do is we try to find out, well, where does the air matter? So the part I skipped, I was just trying to see, well, does it matter underneath the drop as it lands? And so that was some techniques we did for that. I won't go into that. But the next thing that you could ask was, well, if it wasn't underneath the drop, how about above the drop? What's happening in that region above the drop as this thing lands? Is there any physics going on there that's of any interest? And so we're using here a type of photography called Schlieren optics. And so I'm going to what this does is it tries to increase the contrast that you see in small contrast in the air of differences in the index of refraction. So what you see here is a black drop. So that's solid. That's the uninteresting part of this. What you see down below is the black substrate. That's also just there. That's the uninteresting part of this. But what I want you to focus on is this. Now I'm going to stop this here. And you see that behind this drop, you can visualize the wake, right? You see those lines that are coming in from the side. So that's the wake, and that's the kind of structure I want you to be looking at. Not at the black part itself, but these levels of gray around that black region. So that's what the air is doing. So, I mean, I know that you're all upset at night when the bathroom faucet leaks and it keeps you up. But you saw beautiful things about how the thing is breaking apart. And those drops really are kind of lovely. You see that when it splashes in the sink, it also has beautiful behavior in the splash itself, but also in the air around it. And so what I'm hoping is that these kind of studies, I mean, I've tried to emphasize the physics because I'm a physicist and that's what I do for a living. But I also want to kind of emphasize the fact that this emergence of the structure in all of these cases is really showing nature's texture underneath. And this is what we're somehow laying bare. And nature is subtle, and if I can use that word again, wondrous. I mean, it really, I find that it really grabs me and gives me a renewed appreciation for the world around us, and I hope I've been able to share some of that appreciation with you this afternoon. The other point I just want to end with is that, I mean, I've emphasized the science and the experiments, but a lot of these experiments are based on a certain set of tools and a certain set of ideas that come back recurrently throughout of all the studies that we've done. And so the examples are similar tools, the optics and so forth that I told you about, and the concepts, and for the example, the one I'm talking about now particularly is the ideas of scaling that were important here. And this reminds me of this quote by another philosopher, Alfred North Whitehead, where he says, a great idea, and so I'm thinking about ideas like the scaling, is like a phantom ocean beating upon the shores of human life in successive waves of specialization. And I think that really captures something about how we as scientists are able to use the same ideas over and over again, but slightly different, and reach new heights each time that we do this. And so now just to say actually who did all of the work here. And so I have a wonderful set of my group who have been involved in this. I can't show all of their pictures and the different things, but the two up on the upper left did the viscous fingering. The upper right are the people who were involved in the drop breakup. All in the middle row are the splashing. And then the bottom row are the people that I really want to thank tonight because they're the ones who made this place such a wonderful place to work. And so these are my colleagues who have worked with me and published with me in the physics and, in the case of Todd, math department. And without them, they've been my friends, colleagues, but also my mentors. And and for those who are gone, I miss them deeply. Thank you very much.